That about it, guys. I think most of y'all are in the online meeting. Um, Now you can hear me, right?
Yeah, can you?
Right. Okay, so we have some of you guys in at office as well. Sorry, we took a bit of time to set up the meeting. There was some technical delays. So, welcome to the second session of the series of tech talks organized by the Technoid. So, it is basically different than the usual tech talks that we do usually at Search Global. The main difference is that this series is done by the Technoid team. So it's not that we will always take over the tech talks done by Search by Technoid, but this series is also done by us, but it will be done by people who are at the Technoid faction or the Technoid section in Search Global. So welcome to the second session. And this series, the title is Kubernetes 101, done by our very own Dinuksha. So yeah, without further ado, I would hand over the control to Dinuksha.
Hi guys, good evening. So today we are going to talk about what Kubernetes is and why we are using it, like what is the purpose of using it, and whether you guys need that in your project. Okay, so wait. Give us a couple of seconds. Yeah, so thank you. Okay, so before anything, so what is Kubernetes? So we are going to talk about Kubernetes. So what is Kubernetes? So that is not a simple, we can give a simple answer for that. So we can give a simple answer, but it won't make sense for us. So before talking about Kubernetes, we will go back in time and see how IT infrastructure worked back in the day. Okay, let's see. Let's say that you have a project, IT project, and you need a application server to deploy your project, and then you have middleware that you need to again deploy into some particular server or something, and there will be more stuff like that. So to deploy those stuff back in the day, before this cloud, containers, VM, and anything, we had hardware server. So let's say if like number of years back, if it was search, we have our own data center where we have hardware servers. In those hardware servers, we will deploy our application, and then we will have to secure it. And when we need to upgrade, when the usage is higher, we will have to upgrade the hardware servers like manually by us. And because of that, like back in the day, that we didn't need to like scale up a lot because the technology was growing in a way not like what we face now. So that scaling was needed, but it wasn't rapid as what we have right now. So let's say because of that, with the time we started facing number of issues with bare metal hardware servers. Okay, so one of the main issues are it was harder to scale. Let's say your application which is running on the company hardware or your hardware, and that application is being used by 1,000 people right now in the country. Okay, and suddenly with something or because of a marketing campaign or whatever, suddenly the usage is increased by 500 more users. So that is 50% more usage. So let's say, like as a simple example, previous hardware server had 10 GB RAM and 4-core CPU, you can't obviously handle that 50% increase in usage of application. So what you had to do was, you will have to shut down the current setup, and then you have to manually remove the RAMs, and or else like get another RAMs and plug them into the motherboard. It's not simple as that. The hard, like enterprise hardware is not simple as what we have in our house, but in the sake of explaining this, I'm going to be a bit simpler. So we'll have to install new RAMs, and we'll have to change the CPU, and it is like it's a big hassle. Obviously, when we are doing that, by the time, let's say it takes number of hours or maybe days to do that, and by that time your application won't work. Let's say your application is an what do you call like payment application, then your users who are relying on you to pay their day-to-day transactions won't be able to do that. They will go to the shop, and when they're trying to pay, the application won't be working because we are doing an upgrade, and that is not good. Okay, so we are supposed to make their lives easier, so that is going to be a very big issue. So that we can see that the hassle of upgrades, even the software upgrades, we'll have to shut down the machine and do that, which will take some time, and which can cause the same issue. And the high cost, obviously, for the hardware, when we are needing to upgrade, and if something happens and we need to buy the new hardware again because that something happened to it, the cost is higher because basically hardware is very expensive and has a lot of security. So because the whole hardware is maintained by us, we have to take care of the security of the infrastructure. So that is coming to our side, and among all the things, we'll have to take care of the security aspect as well. And we need to have a separate security team because the developers and the engineers might not have the security expertise. So that is another big cost. And the availability issue. Availability issue happens when we are like in the scenario like that upgrade, that availability is not there. So the availability issues are there. And also, if something happens, like sometimes there can be disasters. So if something happens to that, it won't work. So that availability issue is also there. So the solution came like this, like, so we all know about virtual machines. So the solution for this one, so issues were virtual machines. What virtual machines does is, so we have our hardware infrastructure. We might have it by ourselves, or maybe we'll be using someone else's infrastructure. And on top of that infrastructure, we will be having a virtual machine, virtual computers. So that one, so if you can see here, so this infrastructure can be ours, or maybe it is from a cloud provider, or maybe it is from some other provider in your country or in your area that rent us the infrastructure, but we are not using this infrastructure directly. Okay, so above that infrastructure, they have the host OS, which is the OS running on the infrastructure that they have, and on top of that, there's something called a hypervisor. What hypervisor does is they take the host OS and it runs the host on the host OS, and it virtualize the resource which is available on the host infrastructure. Let's say they have 100 GB of RAM. So the host OS will need, let's say, around 10 GB for the host machine to run, and the rest of the 90 GB can be used for these virtual machines, and that task can be done by hypervisor. So hypervisor will virtualize the resources that we have available, like the extra resources that we have in the host infrastructure, and that will be virtualized. And in the virtualized resources, we can install another OS, which will be facilitated by the hypervisor. And then, like when you use a VM, like it is same as the normal computer that we use, normal machine, right? So you can you won't feel any difference, but you will have your own OS, and it will be separated by the host and also the other sister VM, and but only the resources will be shared. And okay, so the scalability. So how this whole thing solve sort of solve, not completely solve, the mitigator basically the issues. Scalability. So let's say you need more RAM in the VM1. Okay. So what you can do is, when you are provisioning a VM, we can let the hypervisor know, okay, I want a 10 GB RAM and 4-core CPU. So we can give the instructions to the hypervisor, and it will allocate infrastructure resources from the host and give us a VM which has 10 GB RAM and 4 cores. So let's say if you want to increase that. So in a scenario where we have enough more infrastructure resources, we can let the hypervisor know, okay, we need to increase the RAM. So we can increase the RAM without having to have more hardware resources. Like we already have the resources, because this will be managed by a third party most of the case. We can rent that more resources and allocate that to our VM. So we no longer we need to go to the shop and get a RAM, get a new CPU, and plug it. Don't need that. We can just ask hypervisor to do that. Okay. And upgrades also like that. We can now do the upgrades easily, but the upgrades like software updates and patches is not that much improvement. But if you're using a VM which is hosted on a cloud service, if the cloud service is managing that upgrades, then there will be an advantage to us. But if we don't have that, if we are using our own infrastructure and running VMs on top of that, we are facing the same issue. The cost will be lower, because in a scenario where we don't pay for this, we are just renting this. So the cost will be lower because we don't have to manage the hardware anymore. We don't have to cater for the security and issues that we face, like we don't have to worry about the disasters and stuff like that. Yeah, and the availability. Because VMs are virtual, we can sort of easily have multiple instances of what we have. Let's say our application backend is previously we had one or maybe two. Okay. Now we can, because previously it was hardware, it is very costly to have multiple instances of our application of the backend or the backend. But now, because this is virtual, this is bit much cost effective, and we can have that, and the availability will be increased rather than what we had previously with bare metal servers. Okay, so as everything goes, our problems will kind of sorted at the moment, but with the time, we will definitely get more problems. So that is what happened back in the day also. Okay, so let's see what are the issues that we faced with the VMs. Okay, yes. The problem is, when we started using VMs, that's okay. But we are evolving, and the applications and our requirements and the technology and everything else is also evolving. So our requirements go up, and our usage, obviously, how much time we spend on our phones, right? How much time? Like, I think 1/4 of the time we are using the phone. That's crazy. So with that, VMs couldn't carry that. So we needed the solution. So okay, those are the problems that you face as a customer. So what technology providers, let's say the application developers or the companies, what they face was, so we have to cater them, like we have to, like even number of VMs we have to cater. And when we are doing that, we realized, oh no, like, okay, let's say we need 10 VMs. Okay, now our usage is higher. Now we need like 20 VMs. So what happened was, so each VM have an OS, right? So for a VM to run, even idly run, we need to allocate resources. Okay, so you all know that for the OS to run, we need resources, right? So those resources, let's say Windows Server, you need 2 GB of RAM, 2 core CPU, and 20 GB of storage, like that. So let's say you have 20 VM and 2 GB of RAM, 40 GB of RAM just to keep the system idle, and 20 GB of storage into 20, 400 GB of resources, hardware storage, just to keep the system idle. That's right, right? So we are paying for that. So that is the resource utilization for the guest OS. So guest OS is taking so much of resources. When we are multiplying, when we are having multiple VMs, that is an issue. So we are paying for that. That's a big no-no. Right? At the end of the day, we have to think about the profitability of the company or the business. So people thinking of reducing these costs, and yeah, so that is one issue. So lack of portability. Hypervisors are specific, like we have VMware, and I think Microsoft has something called Hyper-V. So those number of hypervisors are specific to each other. So you can't take the configurations of a VMware and put that VM on a Hyper-V hypervisor, which is by Microsoft. We can't do that. Those are not portable. And cloud, also cloud specific, like if you're using Azure, and Azure cloud VM configurations are different. And Google Cloud is again different. And AWS again different. So lack of portability is also there. Spin up time is longer. So VMs, they take time to spin up the VMs. When we need a new VM, we have to spin up and turn it on and we see it takes time. Because in this industry, like in this game, like where we need to cater the content or service that we are providing to the user, like where we have to do it in milliseconds. So this might not a big time, but when it comes to this application, that is a big time. And scaling can multiply the cost. So because the scaling happens by multiplying the VM size, we have to multiply the VM. So that can directly affect the cost, like the number of VMs, that it is proportional to the number of VMs basically. Compatibility issue, because the VMs can have multiple OSs and can be from different cloud providers. So as like I told you earlier, the portability like that, the compatibility issues is there. We can't just use it anywhere. So now we need a solution for this also, right? So let's see. So for that, people came with a solution called containers. We all have used it, right? You know, Docker containers, and there's something called Rocket as well. Rocket as well. So Docker is the most popular one that we use. So Docker came as a solution for the VMs, but they don't take this as we will stop using VMs. We will still use VMs, But for the application deployments, we will use containers in a different way. Okay, so let's see how it works. Okay, so before that, we will see the differences of VMs and containers. So if you see this diagram, you can see this is a bit similar, and we are missing some stuff. So we have the host infrastructure, which will be on-premise infrastructure or a cloud infrastructure. And then we'll have host OS. You know the host OS, like the host OS of the host infrastructure. And then for the VMs, we have hypervisor. For the this one containers, we have something called container runtime or container engine. Okay. And then VMs and containers. VMs have the guest OS, we all know, and binaries and libraries. You know that as well. We have to install what are the binaries and libraries that we want to our application to work, and then we have our app, right? It's a node app. You have that. And for the containers, you don't have a guest OS. You have binaries and libraries, and that you install all the binaries and libraries that you want for your node app. This is an example, and then you have your node application. So how is it going to work? In the VMs, we use hypervisor to virtualize the infrastructure, and on top of that infrastructure, you are installing a guest OS and then treating it as a normal computer or a system, right? On the containers, you have container runtime and host OS and directly binaries and library. So where is the OS? Like, how is it running without an OS, right? You need to have an OS to run, right? Like we all know. Just hardware, like without an OS, it's just hardware, we can't do anything. We'll have BIOS and stuff, but we can't do our work now. So what happens in container runtime is container runtime can access the kernel of the host OS and virtualize that kernel and the binary, some of the binaries and libraries which is available in the host OS, and then use that in the container. So that one you virtualize the resources. This one also you are virtualizing the resources, but it is dynamic. Okay, it is not specific like that. We can, like here we say, okay, we need 10 GB of RAM. We don't say that here. We can say that here also, but we are not doing like that is different. Here, what we are doing is not like the main thing that we do is we are going from the like OS layer also, like the kernel layer. We are using the host kernel for our containers to run their whatever the applications or the stuff that they want in their container. So if the host OS is Linux, we can run Linux containers on the host OS on this this scenario. Okay, so you might be thinking that you may have installed Docker for Windows in your Windows computer, right? And you have ran Linux containers on top of that. So you might be thinking like, I don't have a host OS where the Linux kernel is there, but I'm using Linux container. So how are they getting that kernel? So what happens in that is when you install Docker for Windows, that is the container runtime, basically container ng, or you call it Docker daemon. So what they do is like when you are installing it, it will install a Linux VM inside your computer, and then that Linux VM has the host kernel, and the containers can use those host kernel there. So you don't have the guest OS anymore. You have exactly what you want in the container. So if you guys have logged into a container, like you can exec into the container, like if you like go into a container and use the command line, you can see that the most containers are Linux containers. So you can see the file system is the Linux file system, right? So what they do is when they are virtualizing the host OS and kernel, they will have their own file system. The file system will be separate from each other, isolated, and so you can easily use the containers to do what the stuff that you want. It won't be colliding with other containers because the file system is separated. Okay, and so it seems very good, right? Because containers are lightweight because we don't have that OS headache that we had, and we don't have to specifically allocate resources like the RAM and CPU that we want, and that's great. And also the great thing is container supportable. If you have defined the container in your computer, it will work anywhere in the world. If the Docker, like if you are using a Docker container, it will work anywhere in the world if the container runtime is Docker. It will work anywhere, on Linux, on Mac, on Windows, whatever, it will work. Definitely it will work on any cloud provider, like because are you like defining when you are defining the Docker container, it is done, like that is portable. So that's it. You don't have to do OS specific configuration. You don't have to do cloud specific configuration. So that's very great because that is like minimizing our work, and also it is efficient because we are using less resources to get the work done, and it is modular. So you guys know, right? Like to use a container, you have to first let's for this example, for the whole thing, we are taking Docker as the container type. So when you need to, you write the node, let's say node application. Now you want to deploy your node as an Docker container. Also, one thing, you guys can ask question anytime you want. Okay, anything that you come across, you can ask. And once you are done with the code, you can write a Docker file. And Docker file is the place where you give instructions how to make a Docker container using the source code that you wrote. Actually, you are not creating a Docker container, you are creating a Docker image, which is like a blueprint, which will be used for creating Docker containers later in the deployment. So you write the Docker file, you say, okay, use node, which version that you want, this version, and copy these files from my source folder and into your container, and run these commands, npm commands and stuff like that. What you do, like what you write on a local machine to run your application, you change bit of that different because the application environment is different, and you run it inside the Docker file that will be stored as instructions in layers, and it will create something called Docker image. Okay, so then we can deploy those Docker images in something called image repositories. So Docker have their own container repository called Docker Hub, and we can use that also. And Docker Hub has like all sorts of Docker images that we can use from all the providers that you can think of. And then for the private repositories, we can use Google has their Google Container Registry. AWS has, I think, Elastic Container Registry, if I'm correct. And then Azure also has their own thing. So we can create our own Docker registries as well, image registries as well. So once we write a Docker image, Docker file, and create a Docker image and deploy it to our container registry, that will be like we are deploying a specific version, right? That will be used as a blueprint to create containers in the deployment, like deployment infrastructure. Okay. Then that it will always be taking that Docker image to create more Docker containers when needed. Okay. So let's say you have your node backend and you create a Docker image using the node backend. Okay. And the Docker image will be stored in a container registry. And now you want to deploy that. Previously, we did was in a VM, we can deploy manually, right? We can run the code and deploy it manually to run as with what happens in like exactly like in the local computer. Here, what happens is it will run as a container, and how container takes the source code is that is not going to take the source code from your repository or nothing. It will get the Docker image and use that Docker image, like Docker image of your node application, and use that as a blueprint and create running functional instances of your application as a Docker container. Okay. So you can have one instance of your application, 2, 3, 4, 5, 6, whatever. It will be very lightweight and it will be very easy to have multiple containers. And also, like immutability is once the Docker container is created, image is created, you can't change it. The container, you can't change it. Like you can change while it is running, but if that container fails, and if container fails, and again when you are creating a new instance using the Docker image, it will come back to the correct state that we wanted. Okay. Yeah. So then, so the containers, we treat them like cattle, not like pets. So let me explain that to you guys. So what happens here is the cattle is like in farm, we have cattle of cows, right? So there will be like hundreds of cows in the cattle. And for the pets, we have them in our house. Let's say you guys have 3 pets in the house, like normally we have 1, like let's say you guys have 3. So all those 3 pets, you have 2 dogs, 1 cat, you know the names. You love them. You know the names, you love them. You individually care for them. You check whether they eat. You check whether they like everything, like whether they are hungry. So you take care of them individually, right? So that is pets. But cattle. So let's say you have hundreds of cows in the cattle in your farm. I don't know whether they give names, but ideally, as for the example, ideally, like we won't know the names of those 100 cows, right? Like there may be a code, like tattooed. I don't know what they call it, like tattooed or whatever in their skin, and you won't treat them like your pets, right? Because that is cattle. Because the number is very high, we don't treat them individually. We don't individually love them, right? So containers are also like that. So remember, we had VMs back in the day. So let's say search. We have 3 VMs. So we know that, okay, 3 VMs. We have to take care of that. We have to check whether, okay, the usage is going well, and whether we'll have to come in the morning and check whether there are intrusions and stuff like that, because there are 3, we can take care of that every day. Okay. But let's say containers, as I told you guys can like feel that, okay, the containers are in very big numbers, like 10, 20, 100. So we can't do that for the containers. Containers are very scalable. So with the usage, it can scale very up. Once that is done, how can we control like 100 containers, like let's say 100 billion, like that. We can't. So containers, we can't take care of those very big number. So for that, we need to find a way to handle the capital. So for that, we have something called container orchestration. Okay, so because with the time, the usage increased and our infrastructure, the way we deploy our infrastructure changed. Now we have containers, and meanwhile, the software architecture also changed. Now we have things called microservices. Back in the day, we had monolithic applications. We have everything in one single backend. One single backend to have all the components there. So in order to change one part, we have to update the whole thing. Now we have made it modular. We have divided the whole backend into number of pieces, sometimes hundreds of pieces. And because of that, everything changed. Now you know that we can't put them in a one VM. So we can't put them in a one container also. So because now we have number of services, so we need to have hundreds of containers to run our application. So for that, we need a way to control that. So how to control that containers and their behavior is known as container orchestration. So there are a number of solutions, providers that help us do that. One is Docker Swarm. Docker, the company Docker, they have their own container orchestration service called Docker Swarm, and Apache has Mesos, and Google came up with something called Borg back in the day around 2013, 14, and then the Borg was created to control their own resources and infrastructure. They own like Google's infrastructure. To control their deployments, they created something called Borg to use internally. And with the time, they realized, okay, we can give that to the public as well. So they rebranded it as Kubernetes, and then they released it. So now we are using Kubernetes, and now we can talk about. Sorry, I missed this slide. We are now using Kubernetes mostly, in most of the scenarios in the world. For the container orchestration, most of the people we are using, most of the project we are using Kubernetes, and it's easier than others as well. Yeah. So let's talk about Kubernetes. So when you think about Kubernetes, it is a way it is a framework which will take care of the deployments, how it is scaled, how we are giving the resources to the containers, how we can schedule how the service is going to spin up and spin down, and also how the updates are, how we are going to give updates, and especially we can give updates without affecting the service at all. Like in the previous scenario, we went to the shop and we can't pay and we had to come home back. So with Kubernetes, that's what happened. Even with the update happening in the time, we will be able to use the previous version until the next version is ready. Okay, so let's look at a Kubernetes cluster. Let's see how it is working and get a rough idea about it. Kubernetes comes as a cluster. So inside that cluster, you can deploy your application. And okay, so the Kubernetes has two main types of clusters. That in that blue dotted line square, you can see control plane, right? In the control plane, we have master nodes. Master nodes are node is also a computer, which is a VM. That VMs which is running underlying the node, underlying the control plane. Control plane is running on computers, which are VMs. Okay, So control plane is running on the master node, which is one type in Kubernetes. And then we have worker nodes, master nodes and worker nodes. Worker nodes are the place we work. Developers or DevOps engineers, software engineers, that is the place we deploy our applications, and that is worker nodes, which will be also like running on node pool. Node pool is a collection of nodes which will be running on VMs. Okay, just think it as a node is a VM. Okay, it will be a pool which will be shared among the deployment. And control plane will be the one who will be handling everything, who will be managing the worker nodes. We have to give instructions to Kubernetes to get what we want, right? So we give instructions to the control plane, and then control plane will take care of the work that we ask them to do. Control plane will also have their own Kubernetes deployments, and we can see in the corner we have the main thing is the Kubernetes API. The Kubernetes API is the interface that we have towards the control plane. So when we have our definitions of what we want ready, we talk to the Kubernetes API and say, okay, I want this Python application deployed on 5 container instances, like that. Okay, so we call the Kubernetes API and say that, and Kubernetes API will then look at etcd, that etcd, we call it etcd, and etcd will have the configurations that actually it's a key value store. So that key value store will have all the configuration that they need, like the state of the deployments, the state of the pods and containers and the node. Everything will be stored in the etcd. And when we give instructions to the Kubernetes API, that will be used. And then we have the scheduler. Scheduler will schedule the jobs that we give them and run them in a orderly manner. And then we have the control managers, cloud control manager. Cloud control manager is the component which will talk to the cloud provider. So let's say we are using Google's Kubernetes engine. So cloud control manager will call to the Google cloud provider's API and then talk with that the resources on Google Cloud and get what they want. So basically, when we use something like Google Kubernetes engine, we don't have to worry about the control plane, because the control plane master node that will be managed by Google. We only have to work and play with these worker nodes. We only can see the worker nodes in managed Kubernetes. Managed Kubernetes means like if the control plane is managed by somebody, let's say AWS, Google, Azure, whatever, that is managed Kubernetes. We don't have to do that. If we are having our own Kubernetes cluster, which will be a big hassle, which I won't recommend anybody to do. Like there are scenarios where you have to do that, but that's crazy. In most, like 99% of the time, we can use the managed Kubernetes to get stuff done. Yeah. So do you guys have any questions in this scenario, like this up to now? If you have, you can ask. No, okay. Sandhu, do you have any questions now? Yeah, and yeah, we'll go to the next part. Yeah. So, as I said, we'll have to work with the worker nodes, right? So let's see what the worker node, like how the application, like where is our application basically running. So we are talking about Kubernetes and pods and deployments and stuff, but we don't know like where are our application, if your Python application, where is it running, right? So first of all, we have node pool. Node pool is the place where like node pool consists of number of nodes, let's say 5, 6, 7, 8, it can grow. And those nodes can be located in number of multiple regions, multiple countries. That can happen because let's say there are 10 nodes, 3 nodes are in US East and another 3 nodes in US West and another 4 in somewhere else. Let's say something happens to one node, we can have like region-wide outages sometimes. So if we spread it nicely, we will have at least 3, 4 nodes running all the time, because we can see, right? Because sometimes even we had back in the like couple months ago, we had YouTube outage and stuff like that, WhatsApp outage, like the worldwide outage, like that kind of stuff we can't basically, definitely we can't solve. But let's say we had a issue in US West, if we have our nodes in US East, will be good because we have half of our infrastructure there. And yeah, so the node pool is a collection of nodes, collection of VM spread across the world. And then we have deployment 1, 2, 3. Deployment can be defined as something like this. Let's say you have an e-commerce platform. You are running an e-commerce platform, okay? And you have number of microservices, let's say 3. One is user service, which take care of the users. And then you have, let's say, inventory management. And then you have shopping cart. And let's say 3, you have 3, right? Those 3 things are 3 different like applications, right? 3 different applications. And that one application can be defined as a one deployment. Okay, so let's say the deployment one is user service deployment. Deployment 2 is shopping cart deployment, and deployment 3 is inventory management deployment. Okay, so you can see in that deployment there are something called pods, and there are 2 pods, pod 1 and pod 2, pod 1 and pod 2, like that. So that means pod is the instance that you are running basically. So your inventory management, let's say it's a Java application, Spring Boot application, let's say, and that Spring Boot application, that one instance can be considered as a pod. Okay, so if you are having 5 pods, that means your Spring Boot application is running 5 instances per pod. Okay, and yeah, so with Kubernetes you can easily like define the deployment so that can scale up or scale down the number of pods that you have very easily, and it won't affect your application runtime. Like it won't affect your services at all. It will scale up, it will scale down to work perfectly. And so we can see also pod is not the smallest component there. So there are containers in the pod, and if you are running the Spring Boot application there, we only need 1 container, right? Right? We only need 1. So here we have 2. It can be 2, 3, 4 as well. So why we need more than 1? Like most, like we can have 1. We can basically like define a container where we have our Spring Boot application and wrap it with a pod and call it a day. Okay. So why we have multiple containers inside the pod? So let's say your Spring Boot backend will be talking to a database, right? And that communication can be directly happen from the pod, like directly happen from the container to the database that you have, right? Or else we can modularize that part as well. There is something called a sidecar container. So you have a main container, which is a Spring Boot application, Spring Boot container, and then you can have a sidecar container, which will be working as a proxy with your database, right? So this is an example for that. So there is no like hard rule to have multiple containers inside the pod, like how you have two or three or like that. You don't have that, but it is advised to have those kind of communications happen modularly with sidecar containers. Another scenario is another example is that have you guys heard of Istio? Okay, so Istio is something called a service mesh. So as I said, in a big application, you have hundreds of, let's say 50, not hundreds, let's say 50 microservices. So it will be communicating with each other. It will be a mess, right? Like to it's a like the community that talking with each other, that mesh is like it's very complex. So we can get a visibility to that using something like Istio. Istio is a service mesh which we will be installing to the Kubernetes cluster, and then it will inject Istio containers inside every pod. Okay, every pod, and when let's say that there are I told like number of services. So your user service have to talk to your core service, and then the core service has to talk to your inventory management like that. So that communication can happen directly. Also, communication can happen in a different sidecar container also. So when that Istio inject the sidecar container to the pod, that can happen, that the communication between services can happen through that. So when that happens, Istio can give us and like service mesh diagram, something give data to us real time and show how the communication happens like real time. So if something doesn't work, when we look at that service mesh, we can see okay, where is the problem that shopping cart is not communicating with the core service like that. So we can use sidecar containers for stuff like that. So now, can you guys see like where is the application is running inside Kubernetes, right? Okay, yeah. So do you guys have any problems until now? Okay, right. So let's go to the next part. So how are we going to? Okay, so we talked about how we are giving instructions, but we didn't say how we are actually giving instructions to the Kubernetes API, so they know what we want, right? So to do that, we need to write manifest files, which is also called Kubernetes YAML files and stuff like that. Manifest YAMLs and stuff like that. Yeah. So this is so we know now what is the deployment is, right? Okay. So this is a deployment YAML where we define what we want to be deployed, how we want it to be deployed, what are the versions, what ports to be opened, and stuff like that. So here we can do the API version, which will be the Kubernetes API version, and the kind that is very important, that is where we define, okay, we need a deployment. Okay, there will be number of YAMLs and deployment in that one. Each kind we have to define, okay, we need deployment, we need a service like that. So deployment and we can put metadata, names, and labels. Labels are very important as well. And the replicas, in the spec, we can define replica. So that means you need 3 instances of this particular application. Okay. And so matching labels and stuff like that. And on the second spec, we have containers. And in that containers, we have a name and we have the image, right? So we earlier talked about container images, where we define what we want. We define, okay, take the source code and create a Docker image. So we define the Docker image there. Okay. So this is in this scenario, they are taking an Nginx image from the Docker Hub, and this is that image and the version of that. And also they are mentioning to open the port 8. Okay. So this is how we define the deployment that we want. And yeah, so let's say, okay, you done this and you create the deployment. You still don't know how to deploy using this, but okay, let's say yeah, done. Okay. So this will spin up 3 pod deployment with 3 pods of Nginx, but we can't access it. It will be running there in a Kubernetes cluster. We won't be able to access it, even though we open port 80. So for exposing the Kubernetes workloads, we have to use something else. Those are known as Kubernetes services. Okay, Kubernetes services will that is also we'll have to define in YAML. They have their own parameters that they want from us, and we can define how we want it. There are 3 types of Kubernetes services in Kubernetes. One is cluster IP. This will give us a internal IP inside the cluster, not a public IP. Inside the cluster, that IP can be used to talk to those services. Okay. And then we have node port. Node port is something, it will be exposed to public, but what happens is, so we have a node, right, work nodes. It will open a specific node port this will be static also, specific node port in the one of our nodes, and it will take the traffic from that node port, and then it will direct that traffic to specific service that we want. Okay. And then we have load balancer. Load balancer will directly get a public IP from the cluster. When we create the Kubernetes cluster, we'll have to give a range. These are the IP ranges that we need, like that we have to do. So we'll get a public IP and assign that public IP to this particular service, and will open the port that we specify. So that will be basically public. Okay. So let's see. So let's see how we define a service. So service, we have the same thing. API version, the kind is service now, because we are deploying a service, and the name is there, and we have a selector. So we connect services, deployment to be able to access by outside. We definitely need a service. So we have to connect our deployments with service, definitely. So we are doing that using connectors, selectors. See, so the app.kubernetes.io app is Nginx. We defined that earlier as well. See that match label app. So using those match labels, we are giving the values, so the service can identify which deployment I should use, like I should export. Okay. So here we don't have, we don't have a type, another parameter called type. In that one, we can define whether it's a cluster IP or a node port or a load balancer. If we don't define it, it will be a cluster IP one, and we will have an internal IP. So this will be a cluster IP one. And in the ports, we have a target port and the pod. Target pod is the target pod of the deployment, not the deployment, like the container running inside the deployment, because we open the 80 port of the Nginx, our target port is 80, because we have to target the port that we are exposing. And then we have the port. The port is the port which will be exposed, like what will be shown to us using the service. So in this case, it's a cluster IP, which will be internal IP, and the 80 port will be there. The traffic coming to that this services 80 port will be directed to the container 80. Okay, right? Yeah. And so that is basically it for the services. You guys cool with it? Okay. Yeah. So now we saw, okay, everything is running inside the deployment. Not everything. There are stuff similar to deployment as well. We have stateful sets. We have daemon sets. Daemon sets are normally for our application and what we deploy, we always use deployment. Let's say if you want to deploy a cron job, Kubernetes has a kind called cron job as well. So we define same as the deployment, and we can change the kind as a cron job, and also we can give a cron schedule that number as well in the Kubernetes YAML. So stuff like that, and we have some other resource types as well, which will be helping the deployments and demo sets that we need and use. Those are config maps. Config maps we use to give environment variable and also a configuration file using because containers are stateless and those are immutable. If we want to change something, we can, if we want to change the environment variable we have control, we can use something like config map. Okay, because container will be always taking the container image as the blueprint, and once that is done, we can stack config map, so we can change the environment variables and the configuration file stuff. Yeah, and we have namespaces. Namespaces are like logical boundaries inside the Kubernetes clusters. We can have categories inside the Kubernetes cluster, which will be a logical, we can have backend as a namespace. We can have front end. We can name it whatever we want. So we can define, okay, these deployments go to this namespace like that. Okay. And then we have persistent volumes. We can attach storage volumes to our deployments, daemon sets, stateful sets, and that stuff inside those volumes will be persistent, and not then we can use the Kubernetes deployments as for the stateful applications as well. So this is an example for the config maps and secret. Okay, secret is something I'll show. So we can see kind is config map metadata star. So if we define the namespace, we can put that in the metadata section. We can write the namespace colon and the name of the namespace. And in the data section, we have environment variables. Player initial length equal 3, like that. Those are the environment variables. When we mount these config maps to the deployments, that containers inside the deployment will get these values as environment variables. So the next one, the game.properties, that is a file. We have that that symbol there, that means it's a file. So that will create a file name game.properties, and we'll write those values inside that file. So we can mount those ones as well. So if we have to give environment variables and also those data is confidential, we can use secrets. Here, when we define that, we have to write encode the value using base 64, and then we have to write that base 64 value here. But for the Kubernetes cluster, the value will be internally visible, so anybody can decode it. But so how to mitigate that security risk is to, like, sometimes we can use stuff like basically everything, and we have defined the volume name here. It will be connected to that using that, and we can get that persistent volume claim and attach that to the volumes inside the deployment. Then that deployment containers will have access to this mount path, and application can store data, and that data will be persistent inside that volume. Got it? Okay. Now, now we kind of know how we define the deployments and other resources in Kubernetes. So let's see how we are actually deploying that. Okay. So let's say you write all the Kubernetes manifest files that you want, all the resources that you want. You have everything in a repository. And how are we going to deploy that to a Kubernetes cluster? So let's say you created the Kubernetes cluster on a cloud provider, let's say Google. You created a cluster, you have the cluster. Then you can then connect to your cluster. They give the instructions very easy. And once we are connected to the cluster, we can use something called kubectl, that is the command line interface. And once we log on to the cluster using kubectl, we can give this command to the terminal, kubectl create -f, and path to the manifest YAML. We can give all the files all together, or we can deploy one by one. Once we do that, it will talk to the Kubernetes API, which is in the control plane. I told you, like master nodes and everything. So it will talk to the master nodes. Then master nodes will take these values and then use that to deploy our applications and config maps, services, and what we want inside the worker nodes of our Kubernetes cluster. Okay, right? Yeah. But this method is not recommended for like complex applications and especially commercial ones. It is not recommended because we can't always go and do that, right? Because the main reason we went with this is to give updates very easily without affecting the services and without affecting the user. So we will have to have a proper way of giving new features and new versions of the deployment. So for that, we can use continuous delivery tools, which will be working hand to hand with Kubernetes. So one is Spinnaker. This was being used by Netflix. They made their tool for themselves, because have you ever come across a scenario where Netflix didn't work? Like, it always works, and their search is amazing. Like, they stream the highest quality of movies, and it always works. We have shitty internet in our country, but still works, right? So their deployments, they manage that using Spinnaker, and then with the time they realize, okay, we can give it to the public, and so that came from Netflix Spinnaker. I like that; it's really good. And then we have Argo CD. Argo CD also we can use to we can give the manifest files for everything, and it will create versions like that will edit. Like, when we can connect our repositories with these services, and when we deploy something new, that they will get the manifest file that we created and edit the versions, and then they will upload, deploy a new version of the deployment. Okay, and we have Azure DevOps Platform, Azure DevOps, Bitbucket pipelines, and platforms like that. They kind of wrap their own things around these YAMLs, because nowadays we don't get to directly work with these Kubernetes manifest files. We can define the in Bitbucket, we can define the Bitbucket pipeline to say, okay, we need to deploy this to Kubernetes. We need to define mainly the Bitbucket pipeline, and they will create the manifest files for you. So if your scale is not like, if your application is not that much complex, and it depends on scenario. If you want the like control of everything, you need to create them by yourself. But in most cases, you will be able to use the tools like Bitbucket, even Azure, and they will create the amounts for you. So yeah. So okay, so now we have a rough, like high-level idea of what Kubernetes is, why we use that, and the next question is whether we need Kubernetes for everything, right? So Kubernetes is very costly. So this depends. We have all the good things about it and also the bad things. It's very complex. If you need to have the expertise to handle this stuff, and also the cost is very high sometimes. If your application is not that much complex, like if you have like 2-3 microservices like that, like not say microservices, let's say you have 2-3 deployments, stuff like that, you might not need Kubernetes. But if you have hundreds of services and your services are mission critical, then it is better to have Kubernetes, but it is recommended to check whether you have like easier ways to do that without spending and wasting money. You will be wasting resources if you have done that. In past past years, like we have seen some projects which are using Kubernetes to deploy very simple stuff and wasting so much of resources, which is not recommended, and also to secure the Kubernetes clusters and stuff like that, you have to have the expertise, and if you are not properly doing that, we are having whole set of new issues. So it depends, like say, but nowadays you can have the good things about Kubernetes and way more relaxation in your mind with new services given by cloud providers. So let's say Google. Google has their own app engine. We will have to just create the repo and define a configuration file and then give the instructions to the app engine that will take that and deploy your application. So underlying that is also running in containers. Maybe they are running on Kubernetes as well, but they wrap around those infrastructure and give us something simpler. So if your requirement is not that complex, you can use App Engine, you can use AWS Beanstalk, and you can have some other. We have say like Vercel for the front end applications, and you have number of solutions that you can use, which is using same underlying technology, but the configuration will be wrapped around their own stuff, which will be very easier for you guys. But if you have a very complex application, if you have hundreds of like very big number of microservices, if you want the control, it is better to go with Kubernetes, but you need to have the human expertise for that, and it will be very good and will be great for your future. Yeah. So yeah, so that's it for Kubernetes 101, and I hope you guys got an idea about why we use Kubernetes, whether we want to use, where exactly our applications are running, and I hope you guys got an idea. So if you have questions, you can ask now. So the silence, it seems like either you have understood everything, else you got any of that. I hope that you got everything that I said, and you got an idea about what Kubernetes is. So in the next time when you get to talk about Kubernetes, you know what that is. Like you won't have to know everything, how to deploy and everything, but it is very good to have an idea, okay, how it is used, why it is used, like whether we want to use that. That's it. So thank you very much for listening to me, and it was a great pleasure, and thank you.